Welcome Algebra 2 students to your video on complex or imaginary numbers. I'm going to be making this video in little snippets I probably will have some background sound effects from a certain 6-year-old, but we just got back from the reptile show that we were at over the weekend, and I'm kind of rushing around to catch up with things I needed to get done. So I've decided to use the Cool Math for Kids site for this one. They actually have a wonderful explanation of the complex number system, so that's what I've decided to use. Let's jump right in. Okay, so Cool Math for Kids has some instructional sections to their website, and I really like their complex numbers lessons. So we're going to start here with what are complex numbers. All right, so far in your math career, you've been working with real numbers, even though some of our answers on math tests have been unreal. See, I told you it was a cute website. The part with the ads is a little confusing how this is going to work with using this, and it's not letting me scroll. There we go at the moment. Okay, so you got all your numbers on the number line, and that's your real number system. And we talked about the subsets of the real number system, your irrational numbers like pi here, that's an irrational number right there. Square root of 3, irrational number. Repeating decimals are rational. You can write them as fractions. Here is one of them, 1.16 with the 6 repeating, negative 1.16 with the 6 repeating. Excuse me. But that's your real number system. So what we're looking at here is our complex number system. And you'll probably remember being told that you can't find the square root of -4. And so you can see right there the square root of -4. Nope, we were told we can't do that because of the negative sign. Because in reality, there's nothing times itself that would give us a -4. And just to remind you of what I'm talking about, I'm just going to use some of this dark section over here. I'll write in this nice blue color. 2 squared, that's 4. And -2 squared, that's positive 4 as well. Almost screwed that up there, didn't I? Now this is -4, but that's because of an order of operations snafu where you apply the exponent first and then you tack on the negative sign. So that's not really squaring a number. So there is nothing squared that will give you -4. And that's the important thing to remember here. That's what complex numbers allow us to do. All right, so the square root of -4 is 2 lowercase I. And that lowercase I is the imaginary unit. What is the definition of lowercase I? Well, lowercase I is the square root of -1. I know. You're already kind of getting that look on your faces. So, I know. It's different, and there are lots of applications for it, and actually that's one of the reasons why I chose Cool Math for Kids is because they have actually some of the cooler applications of it. So let's take a look at what some of those things are. Well, one thing is fractals. Apparently now with complex numbers, we can do a whole bunch of cool things that we couldn't do before. And one of them is making these really beautiful fractals. And yes, math can absolutely be beautiful, and I know you'll all agree with me that these are some pretty cool images. And how that actually works, we'll do a little bit of research in class because, it's not something I'm going to be able to go into in our brief little video. But how that actually works is pretty cool, but without complex numbers, we wouldn't be able to do it. Let's continue to the next page with a little bit more on our complex number system. Okay, so again, the square root of -4 is 2 lowercase I. And so if we break it apart, think of -4 as 4 times -1, and then break apart that radical, just like we do when we're simplifying radicals with only positives inside. The square root of 4 is 2, the square root of -1 is I. And so you'll see here you got a whole bunch of different oh, don't mean to move the window. Come on, scroll for me. Scroll for me. Try again. Sorry for the crappy editing jump there. I couldn't get it to scroll. All right, so just to recap what we're talking about here. So we have square root of -25 is 5i. Square root of -49, 7i. Square root of -13 is root 13i. Can't pop the root 13. You can't find the square root of 13. It's irrational, so we just pull out the I and put it afterwards. Just be careful there that you do not end up putting that I underneath the radical sign. Notice how the radical sign cuts off there. Okay, so complex number is made up of a real number and an imaginary number together. And you can see that right here, real number, imaginary number together. Here's the standard form, A plus BI. So you could have 3 plus 2i, you could have negative 4 plus 5i, you could have 5 halves minus root 3 over 2i. Any of those are perfectly fine. One way that you can apply this complex number system is to find the factored form of the sum of two perfect squares. Now, a difference of squares we've been reviewing. We're going to be practicing more factoring in class, but the difference of squares we've been reviewing. It's a sum of squares that's different. Sum of squares you cannot factor with real numbers, so you actually need your complex number system in order to do that. So we can factor it using our square root of negative 1. Since I squared is negative 1, what we do is we say that that 9, the square root of that 9, is going to be, or the two factors that give me positive 9 are going to be negative 3i and positive 3i. And the reason we want that is that if I have a perfect square trinomial, if I say x plus 3, the quantity squared, a lot of kids try to say that's x squared plus 9. Well, no, it's not. Because x plus 3, the quantity squared, remember, has to be FOILed. And so the reason that we cannot factor a sum of squares without the complex number system is that we don't get this middle term without using the complex number system here, because those terms are going to cancel each other out. So if I FOIL this, the first is x squared, the outer is plus 3ix, the inner is minus 3ix, and that takes care of that. And then the last is minus 3i squared. Oh, excuse me, not minus 3. Hold on, let's fix that. Minus, is it going to let me erase it? Oh, good. Minus 9i squared. And what we notice is, okay, well, I squared is negative 1. So if I squared is negative 1, that's minus 9 times negative 1, which turns into a plus 9. So these middle terms are canceling out altogether. They're gone. And all we get is x squared plus 9. X squared plus 9. All right, what's next? Next is a chance to use our imaginary numbers using the quadratic formula. So in the past, we talked a little bit about using the quadratic formula to solve quadratic equations. I'm having a hard time remembering whether or not I taught you about the discriminant, so remind me to ask you about that in class, the discriminant. But I want you to remember that with the quadratic formula, you have negative b plus or minus square root of b squared minus 4ac all over 2a, all over 2a. And I want you to remember that if you got a negative inside this radical sign before, you just had to quit and say there was no answer. Yeah, not anymore. Now, we absolutely can find an answer. We just have to use our complex number system. So if I get a negative 64, for example, in there, negative 64, square root of that is 8i. We still have the plus or minus, and you can sometimes simplify it a little bit, and there you go are your two answers. And there's going to be a lot of uses for this coming up with solving different kinds of polynomial equations, more than just degree of 2, cubic and quartic and so on. So here's another example like that. Here, let's do this. Maybe what I'd like you to do is go ahead and actually, I think what I'd like you to do is actually copy this down. Sorry for the editing jump there again. Copy this down and try it out on your own. Don't peek. Let me see if I can scroll down quickly before you start cheating. Oh, it reloaded the whole page. Okay, well, it reloaded the whole page. So, that one right there, right there. I want you to copy this and try it out for yourself. Then go ahead and continue your video, and you should be able to see the solution if I can get it to scroll. There we go. So with this one, you end up with a 79 under the radical sign, a negative 79 under the radical sign. So you can't take the square root of 79. 79, I believe, is prime. Let's see. It's not divisible by 7. It's not divisible by 3. Yeah, definitely prime. There are a couple more here to try. Let's wait and do those in class. Okay, so hopefully that wasn't too big an editing jump. We're going to look at some operations with complex numbers. I have 6 minutes to finish this video, and I don't think it's going to be a problem. Starting off, you're going to treat the complex number, the complex unit I, you're going to treat it as if it were a variable. So I plus 6i, predictably, 7i. And then this long, drawn-out, ugly little thing here, we're going to distribute the minus. So we're going to have negative 3 plus 6i plus 5 plus 3i minus 8i. And so that means I have 6 plus 3 minus 8i. Oh, I should have put it in front here. And I have negative 3 plus 5. Okay, let me make sure that's right. Yep, that's right. So that's going to end up being 2, positive 2, plus I. Because 6 plus 3 is 9, minus 8 is going to be 1, so 1i. All right, this one we're going to distribute. So the difference here is that we're not going to think of the I as a variable once we get I squared. Now, normally x times x, x squared, but I squared, remember, I squared is equal to negative 1. And we're going to look at higher powers of I in class. That's one of the ways we're going to apply this and see how we can express the answer when we have a higher power of I. But here, we're just going to distribute. So negative 8i minus 32i squared. Now remember, I squared is a negative 1. So what happens here is I usually just cross it out and switch the sign of that term. So we end up here with positive 32 minus 8i. Excellent. Moving on. Still recording? Okay, so here we have one where we're multiplying two binomials, and we're going to FOIL this. So we are going to first, outer, inner, last this one, and then simplify it. So first is going to be negative 12. Outer is going to be plus 8i. Inner is going to be plus 24i. And then last is going to be minus 16i squared. And immediately I'm going to cross out the I squared, change the sign. All right, so 16 and negative 12 there is going to be 4. 8 and 24i, 8i and 24i is going to come out to be 32i. So that's a common theme there. All right, so this is a good example of looking at how these two things are different, how these two expressions are different. Let's look at what happens when we FOIL this one. So first 6, outer minus 4x, inner plus 3x, and last minus 2x squared, which simplifies to negative 2x squared, if we put it in standard form here, minus x plus 6. Now this other one, if we again FOIL it, 6 first is 6 minus 4i is outer, plus 3i is inner, and minus 2i squared. And there's the fundamental difference right there. It's in the fact that negative 2x squared is negative 2x squared, but minus 2i squared is really a plus 2. And so that's the fundamental difference between the two. Finally, we're going to rationalize some denominators. Now, you might recall, let's think back to some geometry. Think back to some geometry. If I have 3 over the square root of 2, we're not allowed to have that. So we rationalize the denominator by multiplying by a unit factor, a factor that's equal to 1, so anything over itself. And we get 3 root 2, and root 2 times root 2 gives us 2, so 3 root 2 over 2. And that's a common trig expression that we're going to see later in the school year. Gosh, I love trig. Here, instead, we are going to rationalize the denominator by multiplying by whatever I need in order to get rid of the imaginary in the denominator. So I'm going to multiply this one by I over I, which again is a unit factor. It's a factor equal to 1. Now on the top we have to distribute that. So 10i minus 10i squared, so we'll come back to that in a second. And then minus 5i minus 5i squared. Because again, I squared is a negative 1, so immediately I cross it out and change the sign of the coefficient. So I have 10i plus 10, or 10 plus 10i on top, and then 5 on the bottom. Well, I can split that up, 10 over 5 plus 10i over 5. And I'm going to end up with 2 plus 2i. Excellent. Now this one's a little different. This one I cannot rationalize by multiplying just by I, because if I distribute the I end up with an I times a negative 1, and that's not going to work. So instead what I'm going to do is use the difference of squares pattern. So I have negative 1 plus 3i, I'm going to do negative 1 minus 3i over itself. Again, still a unit factor, still equal to 1. In the numerator we distribute, and we get negative 8i minus 24i squared, and immediately, make the sounds with me. Oh, make sure you can see that's a plus. And in the denominator, we're going to FOIL. Negative 1 times negative 1 is 1. Now, because it's a difference of squares pattern, the inner and the outer cancel. I'll just show you real quick by doing it underneath here. 1 outer would be plus 3i, inner would be minus 3i, and they cancel. And that's the glory of the difference of squares pattern. And then there, we'd end up with plus 9. So 1 plus 9. So we end up with negative 8i plus 24, except I don't want to do that. Hold on, let me erase that. Okay. 24 minus 8i, because that's the appropriate way to put it, over 10, which we can simplify. 24 over 10 would be 12 over 5, so 12 fifths. Minus 8 over 10 would be 4 over 5, so 4 fifths I. All right, that's imaginary numbers, and that's a wrap. Hope you guys had a good day with the sub, and I will see you in class.